This is part 2 of Chem Activity number 14, where we're investigating the properties of half-lives. In the first part, we introduced the concept of a half-life in the context of a first-order reaction. We saw that a half-life is a constant for a first-order reaction. We also saw this was another way that we could determine the value and the units for K. So now I'm looking at teaching model number 3 in the table that summarizes the equation for the half-lives and different orders of reaction. You can see the equation already for the reaction order called first. We'll now fill in the equation for the reaction orders 0 and second. I'd like to point out that there's no need to memorize these things because the equations are found in your formula sheet. So I'm just going to bring up your formula sheet. You can see that the equations are listed on the left-hand side, and corresponding to each 0, first, and second order integrated rate law equations are the equations corresponding to the half-lives. And they're represented in the same order that you can match up with the integrated rate laws. I will not change that order, so you should always be able to pick out a 0-order half-life equation, a first-order half-life equation, and a second-order half-life equation. So now let's write them out onto our page. So for a 0 order, it's going to be time 1/2 is equal to the original A concentration divided by 2K. And for the second order, time 1/2 is equal to 1 over the original concentration times K. Now there are ways of deriving this, but this time we'll not derive them. I'm going to ask you to accept them and use them from your formula sheet. But we should take note of the implication for each of these equations. Now, as we mentioned before, the first order reaction has a half-life that's a constant, and this should make sense, and that the half-life is equal to 0.693 divided by K. And because K is a constant at a particular temperature, our half-life will be a constant at that particular temperature. However, if you look at the 0-order reaction equation for a half-life, you can see that not only does it involve a K value, it also involves the original concentration of your reactant. Therefore, the half-life will depend on what is the original concentration. Finally, if you look at a second-order reaction, it also involves the original concentration. Now, we'll see the outcome or the implications for this in a few minutes. One of the other things you may notice is that always in the denominator, there'll be the term K. So that's something to check for to make sure that you write out these equations appropriately. Now, I'd like us to have a go through rearranging each of the equations to solve for K, because once again, these half-life equations can be used indeed to solve for K. So starting from a 0 order, K is equal to, and then rearranging the original concentration of A divided by 2 times the time 1/2. Now once again, I do that, I can easily see that the units for K would be molar per second, because the units, of course, for the original concentration will be molar, and of course the units for time, assuming we're making the measurements in seconds, will be seconds. So molar second, and the -1 is exactly what you'd expect for a 0-order reaction. We've already established, of course, that the units for K for a first order are second, the -1. Just to review, that'll be 0.693 divided by, and then in this case, it's going to be time 1/2. And of course, we'll measure the time 1/2 in seconds, and so this will be seconds to the -1. Finally, for a second order, we can solve for K, and so K will be 1 over the original concentration times the time 1/2. In terms of units, this will be equal to 1 over molar second. So we sometimes show this, of course, as molar to the -1, second to the -1. Units exactly that we would expect for second order. So yet again, another way to determine K, where the units are exactly what we'd expect for the relative order. We have just one last thing to do, really, and that's to make the connection about how half-lives change over the course of a reaction for a zero order and for a second order reaction. Let's look again at the zero order, and again at the corresponding equation. You can see that the time 1/2 depends on the initial concentration divided by 2K. For each successive half-life, the original concentration will be decreasing. In fact, we know it's going to be decreasing by 1/2. So note that the original concentration will decrease for each successive half-life. Now, if you're not quite sure what I mean by this, I'll make it more clear when we do the key questions that follow. So for each successive half-life, we would expect that the original concentration will decrease. If that's the case, it means that the half-life itself will decrease. So we might want to write, next to our zero order, the idea that time 1/2 here is going to be going down for each successive half-life. Of course, for our first order, the time 1/2 will stay the same. We also notice for a second order reaction and the equation for the half-life, we know that the original concentration of A will, just as we saw before, decrease for each successive half-life. So that part stays the same, except in this case, of course, the original concentration is found in the denominator. So this will have a different outcome. If the number in the denominator gets progressively smaller, then the half-life value will get larger. So the time 1/2 for a second order reaction will be climbing for each successive half-life. To see how this might work, let's look at the key questions 1 and 2. So in the key question number 1, for the simple decomposition of A going to products, we can see the successive half-lives of 100, 200, and 400 seconds. What is the order of the reaction with respect to A? And then we're also asked to determine the value and units for K. Now, to show you what's meant by successive half-lives and the actual values, we'll do the following. So the concentration of A, original, molar. And the original, and I'm going to use this in a strange way, the original concentration, of course, was 1 molar. I don't need to write molar again. Let's put brackets around there. After 1 half-life, the original concentration of A will now be 0.50 molar. That is, in the next successive half-life, that's the concentration of A at which the reaction will be starting. After 2 half-lives, the original concentration will now be down to 0.25 molar. The half-life for the original concentration in seconds is indicated to be 100 seconds. Once the original concentration has decreased to 1/2 of its original value, down to 0.5 molar, we now go on to another half-life cycle. And that next half-life cycle takes 200 seconds. The third half-life cycle takes 400 seconds. So we can see that the half-lives are increasing. If we now look back at the equations to solve for half-lives, we can see that when the half-lives are increasing, this clearly indicates a second-order reaction. We don't need to apply an initial rate method. We don't need to use an integrated rate law. It's just paying attention to what happens to the half-lives. Now, in this case, I'm telling you exactly how the half-lives are changing. Sometimes you could be given data in the form of concentration as a function of time. And if you pick out what's happening to the half-lives, you can pick out the order of the reaction. Now we're also asked to determine the value for K. So starting with my half-life equation, 1 over the A original concentration multiplied by K, and then rearrange for K. Again, I remind you, you don't need to memorize the equation, but be sure to pick out the correct one. Now in this case, unlike the calculation of K for the first order, we actually need to select an original concentration of A. And again, it actually doesn't matter which original concentration of A you use, as long as you pick the appropriate half-life. So I'm going to pick the original concentration of A to do this calculation. So this will equal 1 divided by 1 molar times 100 seconds. Again, paying attention to the units. So I hope it's clear to you that the value here would be 1.0 times 10 to the negative 2. And of course, the units would be molar to the minus 1, second to the minus 1, as we would expect for a second-order reaction. So from this very simple data, we were able to determine the order and as well determine the value and units for K. Let's take a look at the key question number 2. In this context, this should be very simple, because now you can see the successive half-lives were found to be 50, 25, and 12.5 seconds. We can easily see that the half-lives are decreasing. Just to make very clear what's going on here, original concentration of A in molar, time 1/2 in seconds. Now we're going from 1 molar down to 0.5 molar, down to 0.25 molar. Note I can predict these concentrations because it's always half of the previous concentration. The first cycle of half-lives based on the original concentration was 50 seconds, then 25 seconds, and then 12.5 seconds. Clearly the time 1/2 is decreasing. So if you wanted to, in a sense, justify how you came up with the order, then making the following statement, that is, the time 1/2 is decreasing, therefore zero order, that would be sufficient explanation. Of course, you can also dissect the half-life equation to really confirm it. And again, this is not something I would memorize. If you understand how to read the half-life equation, as we know the original concentration is decreasing with successive half-lives, the fact that the original concentration is in the numerator in this equation, we know that the time 1/2 should be going down for a zero-order reaction. Rearranging the equation to solve for K, the original concentration of A divided by, and I think I'll put my 2 in front, so it's going to be 2 times the half-life. And so once again, this will be 1 molar, so I'll use the original concentration divided by 2 times 50 seconds. This will be 1 divided by 100. And so actually we end up with the exact same number as the previous rate constant, but clearly the units are different. This will be molar second to the minus 1, corresponding to our zero-order reaction. So this is the last of part 2 of Chem Activity 14. We introduced the half-life equations for the other orders, that is the zero and the second order. We see that time 1/2, the half-life, is not a constant. It does depend on the original concentration for each cycle of half-lives. We can see that we can also determine the rate constant and its units based on the half-life equation. The units are entirely consistent with the order. And we've also, in a sense, found an easy way to determine the order of the reaction if you know the successive half-life times.